Complex zeros in the fundamental theorem of algebra, chapter 4, section 6. So what's a complex polynomial function? Is that one that's not simple? Well, in a way, yes. A complex polynomial function f of degree n is a function of the form f of x is equal to, and that's the whole thing we've said before, where the coefficients are complex numbers. Now realize complex numbers could be real numbers, they could be imaginary numbers, or they could have real and imaginary parts. Where a sub n is not equal to 0, n is a non-negative integer, and x is a complex variable. So wow, so we can even throw complex numbers into the variable. A complex number r is called a complex zero of f if f of r is equal to 0. So we're going to start dealing with imaginary and complex numbers. According to the fundamental theorem of algebra, every complex polynomial function f of degree n greater than or equal to 1 has at least one complex zero. Okay, so if it's a complex polynomial function and the degree is at least 1, it's going to have at least one complex zero. Linear factors of complex polynomial functions. I know this is a bunch of information coming at you. Every complex polynomial function f of degree n greater than or equal to 1 can be factored into n linear factors, not necessarily distinct, meaning that we could have multiplicities, right? Of the form f of x is equal to a sub n, so some multiplier, times x minus r sub 1, times x minus r sub 2, times et cetera, times x minus r sub n, where a sub n and all of our r subs are complex numbers. That is, every complex polynomial function of a degree of n greater than or equal to 1 has exactly n complex zeros, some of which may repeat. So whereas we were talking about our earlier polynomial functions, we said there was the possibility that they could have less real zeros than the degree. Now when we're dealing with complex polynomial functions, there will be the same number of complex zeros as there is the degree. Now some of them may be repeating, so our multiplicity may be greater than 1. Conjugate pairs theorem. Let f be a polynomial function whose coefficients are real numbers. If r equal to a plus bi is a zero of f, the complex conjugate r bar is equal to a minus bi is also a zero of f. Remember how I mentioned that if you have an odd polynomial, odd degree polynomial, that first of all polynomials could be broken down into factors that were either linear or irreducible quadratics. And I pointed out with that if we had an odd degree, then we had to have one real zero in there, at least one real zero, because there were these other two that worked together from that irreducible. That's what we're talking about now. That irreducible quadratic is made up of two complex zeros or two complex factors, and those factors are complex conjugates of each other. So if I know that 3 plus 2i is a factor of a polynomial, then 3 minus 2i must also be a factor of that polynomial. A corollary to that, which is just a related fact, a polynomial function f of odd degree with real coefficients has at least one real zero, right? Because each of the irreducible quadratics has to give us 2. It has to give us these complex zeros, and the complex zeros always come in pairs. Then if you have an odd degree, you got to have at least one real zero because there's no second one for it to have as a pair. Well, let's look at that. Complex polynomial functions. Find the complex polynomial function with a degree of 3 and zeros at x equal to 4 and x equal to negative 2i. Well, we know it's third degree, so it's got to have 3 zeros. We know one of them's at 4 and one of them's at negative 2i. Well, that negative 2i is a complex 0. So therefore, the complex conjugate of it, remember that's basically 0x minus 2i. So the complex conjugate of that would be positive x plus 2i. Sorry, 0x plus 2i. So therefore, our third 0 is going to be x equal to positive 2i because of the conjugate pairs theorem. Therefore, we have factors of x minus 4, x plus 2i, and now x minus 2i. If we multiply x plus 2i times x minus 2i, remember that's a special product. That's the product of a sum and a difference. It's the square of the first term minus the square of the second term. So x squared and then 2i squared is 4i squared. But then remember that when you're dealing with imaginary numbers, I squared is equal to negative 1. So negative 4i squared turns into positive 4. So we have x minus 4 times x squared plus 4. Multiply that out and we get x cubed minus 4x squared plus 4x minus 16. Let's find the zeros of the complex polynomial function. So now we're going to go the opposite direction. F of x is equal to x to the 4th plus 26x squared plus 25. Oh, gee, Mr. Davis, this doesn't look very pretty. And we've got this, we're talking about a 4th degree polynomial. It's not even odd, so we don't even know that there's going to be a real 0 to it. But I do notice that it's going down incrementally, x to the 4th, x squared, x to the 0. So I notice here, I can use substitution. If I let u equal x squared, I can turn that into f of u is equal to u squared plus 26u plus 25. Well, I can factor that. That's u plus 25 times u plus 2. I'm sorry, u plus 1. Now that I've factored it that way, I can substitute back in for u. So x squared substituted in for u gives me f of x is equal to x squared plus 25 times x squared plus 1. And I look at those and go, but Mr. Davis, I can't factor those. Well, you can with complex because if we look back, I'm going to bounce back quickly here. If we look at this, we notice that when we're dealing with the difference of squares, the plus or minus, those complex conjugates, it actually gives us, with complex conjugates, it gives us the sum of squares. So if you see something like x squared plus 4, then you just know that it's going to be imaginary. So that's got to be x plus 2i, x minus 2i. If I saw x squared plus 9, x plus 3i, x minus 3i. So if you've got perfect squares, it's still a special product, but because it's a sum instead of a difference, then we know that it's got to be imaginary. They're complex conjugates. So coming back to where we were here, we have x squared plus 25, x squared plus 1. 25 is a perfect square, 1 is a perfect square. So that's got to be x plus or minus 5i and x plus or minus 1i. So x plus 5i, x minus 5i, x plus I, x minus I. So our complex zeros are going to be at x equal to plus or minus I and plus or minus 5. So it takes some thought. We have to get used to the fact that when we're dealing with complex numbers or complex conjugates in this case, that the difference of squares, where we're used to the product of the sum and the difference, actually becomes a sum of squares. So anytime you see a sum of squares, you know you're dealing with conjugate pairs. And there we go.